Great. Thank you so much. I'm really pleased to be talking to you about this today. So as I said, just let me know if you have any questions. And because I'm going to be talking plenty about CMB polarization, let me begin with a very quick introduction. So what telescopes measure are the Stokes parameters of linear polarization, Q and U, which can be extracted just by differencing different orientations of the polarization filters. But in order to connect with theory, it will pay off to speak in terms of scalar E and B modes, which unlike Q and U don't depend on coordinates. So E has this parity even pattern, whereas B is parity odd. And the interesting thing about B is that in the primordial CMB, that is before it gets lensed, any primordial B modes are expected to have been generated by primordial gravitational waves generated during inflation. So it's widely regarded that detection of primordial B modes would be the smoking gun of inflation, and measuring their amplitude, which is parametrized by the tensor to scalar ratio R, basically tells us the energy scale at which inflation took place, and then opens the door to more insightful probes. And we have these constraints that R is below 0.07, but there is probably good physical reasons why we could expect values higher than 10 to the minus 4 or so. So this is a really hot topic in observational CMB science at the moment. The other very interesting property about the primordial CMB is that it is largely a statistically isotropic Gaussian random field. So very simple statistics. But these statistics get distorted as the CMB gets gravitationally lensed by the large-scale matter distribution of the universe. And the effect can be understood as a remapping of the unlensed fields, which I denote without tildes, by some deflection angle alpha, giving you the lensed fields, which will have tildes throughout this presentation. And under the Born approximation, which is a very good one here, you're just taking the deflection along the unperturbed path. The deflection angle is the gradient of a lensing potential, where the lensing potential is an integral along the line of sight of some geometric kernel with the Weyl potential, which in GR is just the Newtonian potential sourced by the matter fluctuations. And therefore, you can immediately see that the lensing potential is sensitive to geometry, sensitive to gravity, and anything affecting the growth of structure. These deflections are actually quite small, of order arc minutes, but they're coherent on large scales, on degree scales, which is the angle typically subtended by the dominant structures causing the lensing, which are typically 100 megaparsecs in size. And that angle is the one they subtend when you put these structures halfway to the last scattering surface, which is around a redshift of 2 or so. And that's where lensing is most efficient. You can see that the lensing kernel is very broad, with contributions going all the way down to recombination. So this degree scale corresponds to the peak in the deflection angle power spectrum at an L of 50 or so. And another remarkable thing about the lensing potential is that, perhaps you can see it from this plot, it receives contributions from a very wide range of redshifts, but most of them are actually very high. So you can calculate it very accurately just in linear theory. At the map level, this is what lensing looks like. So here I'm toggling between simulations of the lensed and the unlensed CMB for the temperature and E and B polarization. Notice that the deflections are indeed coherent on pretty large scales. These frames are like 4 degrees on a side. And an interesting point is that this very well-defined scale in the CMB, the acoustic scale, which gives, which maps to the peaks in the first big peak in the CMB spectrum, gets shifted to larger or smaller scales depending on where the matter is. So when you take the power spectrum of the entire sky, the effect is that the acoustic peaks of the CMB power spectrum get blurred out. So here I'm showing the difference between the lensed and unlensed CMB spectrum. The effect is more acute for the E mode polarization because the primordial E mode spectrum is peakier in itself. But perhaps the most important thing about lensing is that it gives you a B mode, even if there was none from recombination. And it does so because although the Q and U vectors, the directions are preserved, it kind of shifts around the vectors, and some of that primordial E leaks into B. And I'll be coming back to this later because this is a big source of noise for searches for a primordial B mode.
Can I ask a question quickly?
Yes, of course.
Do you know exactly how these sort of simulations are made, going from the sort of mock TE and B to the lensed ones?
Yeah, I mean, typically you simulate a Gaussian background CMB, you simulate a Gaussian lensing potential, and you just deflect one with the other. Of course, you're doing this on a grid, so you need to use some interpolation scheme, but the error is usually pretty small.
Right, so you really are moving by this alpha angle,
yeah,
each patch. I see. So you generate some non-Gaussianity, I suppose, by doing that.
Definitely, yeah. I'll be coming back to that in a second. Yes. Thank you. Yes, so I mean, the effect of lensing has been detected in the power spectrum already, but actually there's a much more sensitive probe, and that's how lensing was first detected, is the trispectrum, or the 4-point function. So as I didn't see who was speaking, but was it Alex?
Alexander, yeah, hi.
Yeah. So as Alex just pointed out, yes, so if you could fix the lens and average over the background CMB, lensing would give you non-Gaussianity. Yep. So if you could, as I said, fix the lens, average over the background CMB, you pick up something that is proportional to the lensing potential. And that wouldn't be there in the absence of lensing because the background, the unlensed CMB is just statistically isotropic, so scales are uncorrelated. So what we do in practice is look for locally anisotropic correlations between pairs of CMB fields, and this is called the quadratic estimator of Okamoto. And that lets you extract the phi mode coupling the pair of fields. And there's a nice interpretation in real space, which you can see if you Taylor expand the lensed field to leading order. Notice that lensing introduces a dependence into the lensed CMB on the gradient of the unlensed CMB. So what the QE is really doing is just correlating the small scale anisotropies with a filtered version of their gradient to try to extract this grad phi here. So you can reconstruct lensing in this way, take the power spectrum and probe the lensing power spectrum and the uncrossed correlations, which is actually a very powerful probe of the growth of structure because it can be used to break the degeneracy between models that give you the same angular diameter distance to last scattering. And in particular, you can probe the sum of the neutrino masses, you can probe curvature, dark energy, dark matter, etc. And in cross correlation with low redshift probes, you can constrain primordial non-Gaussianity based on scale dependent bias or calibrate weak lensing estimators. So it's really great that we have increasingly accurate measurements from plenty of CMB experiments, including Planck, which reported a 40 sigma detection. And so here, this plot shows the Planck measurements in gray with the SPT measurements from the ground in red. And the remarkable thing is that, Planck measures this on 70% of the sky, but SPT is able to have, comparable error bars from just 1% of the sky. And the reason is that they really drill down in a patch and probe many, many more modes on very small scales. So the prospects look really great from the graph. But this is actually a complicated measurement because there's many biases affecting the procedure. I'm just listing some of them here. So basically, there's the N0 bias coming from the disconnected part of the 4-point function, and this would be there even in the absence of lensing. There's also the N1 bias, which is first order in lensing, and it comes from all the non-primary couplings of the trispectrum that respond to lensing but don't have a nice response for our purposes. That they don't let us reconstruct lensing, but rather just add noise. And these two are large, but they can be simulated very accurately and subtracted from power spectra, for example. And there are also beam-related and gain-related systematics, which are quite small for the time being, or biases from non-Gaussian galactic dust or synchrotron foregrounds, which I'll be coming back to shortly. And these can be mitigated to sufficiently low levels by just including the foreground power in the filters that you apply to your fields before reconstruction to downweight those scales. And also there are biases, which are small for now, from the non-Gaussianity of the lensing potential itself, which are usually neglected because, as I said earlier, like the lensing potential comes from such high redshifts, and because you're integrating along the line of sight, so you expect quite extensive Gaussianization, let's say, by just the central limit theorem. So these corrections are of order 0.5% for current experiments and much smaller than other sources of error. Totally negligible until we reach a noise level of 1 microkelvin arc minute in temperature, which we won't be doing for, I don't know, 15 years or more. So what I'm going to be focusing on in this talk is the bias from extragalactic foregrounds, which is the largest source of uncertainty and bias for current experiments. So the idea is that for the next decade, it's the temperature and isotropies that are going to provide most of the information for reconstructing lensing. And this will be true for SPT-Pol, Van Act, and the Simons Observatory. And the problem is then that the microwave sky in intensity looks quite complicated at microwave frequencies, because among other things, it has large contamination from the thermal and kinetic Sunyaev-Seldovich effect from clusters and the cosmic infrared background of dusty star forming galaxies, the CIB. So when you build your quadratic estimator of lensing based on a pair of observed temperature fields, yes, you input something that is actually lensing, but you also input foregrounds, and those can potentially be correlated with phi as well, because clusters and galaxies follow the underlying matter distribution. So when you take the power spectrum of these reconstructions, you get a term that indeed reconstructs lensing and also contains pure lensing biases, but you also get this primary bispectrum bias. And the reason this exists is because this left leg reconstructs lensing, and that correlates with these two foreground inputs, right? That's a bispectrum. There's also the secondary bispectrum bias, which perhaps doesn't have as clear a physical interpretation, and a trispectrum from the foregrounds themselves. You can also have a bias when cross-correlating with low redshift matter tracers for the same reason I said earlier, that that your galaxies trace the matter, and so do the foregrounds. So you have a bispectrum here as well. So
can I ask a question here? Why some term you call them bispectrum and some term you call them trispectrum? Can you walk us through the number of...
Yeah, the reason I'm using these quotes here is because it's the standard of how people call them. But so here, this one that I call primary bispectrum bias, this quadratic estimator here, this just reconstructs phi, right? This actually does an unbiased lensing reconstruction. So then you have a phi, true phi cross quadratic estimator just from the sources. So you have like a 3-point function in kappa, because this S is actually tracing kappa, right?
Yeah, okay.
So this contains kappa, and this contains kappa, and this contains kappa. So it's a 3-point function.
Good.
Okay. Thank you for asking.
Thanks.
Okay.
Can I ask another quick question? Sorry.
Yeah.
Do these things arise because of sort of the bispectrum due to nonlinear large-scale structure growth, or is this something else?
No, it's something else. Indeed, you can have such bispectral biases from the nonlinear stuff, and Anthony Lewis in particular has done a lot of work into that. The answer is that they're negligible for the time being, but this one is just from the Gaussian part. Yeah, this one is.
I see. Okay. Yeah.
Yeah. Yeah, so these are the largest source of error for current experiments. They're very significant. And you can see that in these panels here. So here on the left is these biases coming from the TSC and the CIB for the SPT experiment for, you know, the analysis prescription where they impose a minimum scale at L max of 3000. They say we're not going to go below that, you know, to smaller scales because that's more contaminated and we're just going to bias our results too much. But even then, you can see that the biases are at the level of several percent in the power spectrum. And, you know, you can mask, but you're still dominated by the diffuse and resolve component, and that's what's shown here. This includes a masking prescription, and you can have the same biases from the KSC, and you know, this is from a different paper from Ferraro and Hill for considering the case of a stage 3 CMB experiment like the Simons Observatory and experiments that will be coming online in the next couple of years. And you can also see that these biases are very, very significant. So unfortunately, frequency cleaning arguments are not very useful in this case, perhaps because from the ground we don't have that many channels to observe with. But so the basic idea of frequency cleaning is that, you know, the CMB has a different frequency spectrum as the other contaminants. So if you observe in many channels, you can form, for example, a linear combination that nulls some of the foreground, so that maximizes the signal to noise or something. But if you were to simultaneously null TSC and CIB, in this case, your noise would blow up by a factor of 50. And it's actually useless for the KSC because the KSC has the same SCD as the CMB. So people have suggested mitigation techniques. Perhaps the most commonly used one is to simulate you know, these extragalactic foregrounds, apply your reconstruction algorithms to them, calculate therefore what the bias is at the power spectrum level and subtract it. People have suggested, you know, bias hardened estimators, which means that you can basically derive the quadratic estimators, but optimized for foreground reconstruction, assuming some knowledge of the statistics of the foregrounds. And then you can form a linear combination that nulls the bias, but at the cost of increased noise. And generally these bias hardened techniques don't work so well for the secondary bispectrum bias, for example, or the trispectrum bias. And they fail in particular when the sources are clustered. You can also clean the gradient leg of the quadratic estimator. And the reason you can pull this off is because the information content of the gradient of the CMB is pretty much saturated by an L of 2000 or so because of silk damping. And that's pretty relatively large scales compared to what ground-based experiments can probe. So you can clean that leg only without paying much in terms of noise. And finally, there's this nice concept recently introduced, which is to rederive the quadratic estimator, but expanding out the angular dependence into multiples. And the interesting thing is that if the source emission profiles are azimuthally symmetric, which is probably a good assumption for, you know, for clusters, for example, then you can show that only the monopole of the estimator is, responds to the foreground. So you can just discard that part and use the shear component only, for example. And that contains like 60% of the signal to noise of the quadratic estimator, for example. And this is promising, but it's yet to be applied to data. But the takeaway from these mitigation techniques is that generally you incur a noise penalty and they're suboptimal if the sources are clustered. So this is what motivated recent work of ours that's still ongoing, where we try to calculate the biases analytically as a function of experimental sensitivity, resolution, point source masking schemes, etc., using the Halo model. So we can nicely understand the clustering effects, sorry. And we actually, harnessed also the azimuthal symmetry of the profiles to reduce the lensing reconstruction calculation of the quadratic estimators to one dimension. And we can do this, we can do them now really, really fast using the FFT log algorithm, which is a technique for very fast discrete Hankel transports. And we get a factor of 10 to the 4 speed up compared to the usual calculation of the quadratic estimators. And what we, our analytic method that's shown here for the case of TSC biases to SPT looks very, very similar to what the simulations show. So we're very happy about this. And the nice thing is that in addition to calculating the biases, you can also calculate the associated uncertainties by, marginalizing over pressure profiles or HODs or you name it. And, this is a bit speculative, but I was thinking that perhaps you can just use the optimal quadratic estimators for Lensing reconstruction down to smaller scales than you would usually do because of fear of being too biased. And in that way, you would obtain an optimal reconstruction of the Lensing component, but with a large bias. But if you can accurately, calculate them analytically like this and actually understand the uncertainties involved, perhaps you can still correct at the power spectrum level and really get improved statistical power on constraints on the Lensing power spectrum and cross correlations. But again, this might be a bit speculative. I'd be happy to hear any comments from you. But now I'd like to switch gears a little bit and talk about the delensing of CMB B modes. So as I explained earlier, it's very interesting to look for a primordial B mode, which peaks on large angular scales, right? But unfortunately, you get this lensing part that comes from the conversion of primordial E into B. And on large scales, this lensing B mode comes about by basically deflecting small scale E modes with small scale lenses. That's what this plot shows here. And that's why you can't pick up any correlations on large scales. So you get this white noise tail of power that looks like an experimental noise of 5 microkelvin arc minute, which is in the ballpark of current experimental noise levels. So you have this noise from lensing on top of the noise from your experiment, on top of the noise from foregrounds. So if you want to look for a primordial signal on large scales, you actually need to do something about all this variance. And that's a procedure called delensing. So the idea is that, if lensing operates by this forward remapping of the unlensed fields, so sorry, here P is just the CMB polarization, okay? So lensing remaps the unlensed fields by alpha. Delensing is remapping the lensed fields back by the gradient, by the inverse of alpha, which normally is just taken to be minus alpha. But the difficulty here is that, I'm gonna go back a second, we want to measure the large angular scales very accurately because that's where the primordial part peaks. But in order to delens, we need small scales. So it's very difficult to have a telescope that can do both. So what is going to be done for the next generation and probably beyond is to have small aperture telescopes surveying the large scales with little noise. And then you build a template of the lensing B modes using observations from a large aperture telescope, really, drilling into a small patch of sky. Sorry, that's not quite true. But the point is that that this large aperture telescope has a small beam. So you can really do the lensing reconstruction very well. And then you subtract that from your observations and you get your delensed field. And how do we build this template? Well, if in nature, the lensing B mode comes about as a convolution of unlensed E with the true phi, we can build a template to leading order by using the same convolution operation on filtered observed E modes and a filtered proxy of phi that we can reconstruct either internally from the CMB or use the CIB or some other traces of the matter. And this is what SPT used in their first demonstration of B mode delensing. But you can also do this non-perturbatively by observing E modes, remapping them according to your estimate of the matter distribution, and then finally extracting just the B mode part. And this is what Planck and Polar Bear have done more recently. So why is it convenient to do this? Well, as I said, it optimally harnesses the strengths of the two telescopes involved. If you use the gradient, I will interchangeably be saying linear order with and gradient order. It's the same thing. So if you use this linear order template, it's more analytically transparent, of course, but most importantly, the reason why people have been using these templates is that they're assumed to track the true B modes very accurately. And the reason for this assumption was that the power spectrum of this leading order template looks very, very similar to the true one. Corrections are below percent level. But the only reason this is so is that there are extensive cancellations between two large terms next to leading order, which I'm showing here. So this is from a paper that we'll hopefully submit today or tomorrow. So these two large terms are of order 10% of the total lensing power, which is shown in black. And each of these two large terms is shown in orange and blue. Dots are simulations, and lines are analytic calculation. So they cancel out really precisely so that residuals at the power spectrum level are indeed very small. But crucially, if you were to delens using a linear order template involving unlensed or delensed E modes, which people have often said in the literature would be an interesting thing to do, you only remove one of those large terms next to leading order, and you're left with this delensing floor here. So everything in this slide is in the noiseless scenario where you have access to perfect E modes and perfect pi. So you hit this delensing floor at order 10% of the total lensing power. But perhaps more interestingly, if you form a non-perturbative template from observations of E and you delens, you remove the other term. Notice how similar these two are, and you hit the same order 10% delensing floor. But the neat thing is that was very unexpected, is that if you actually plug in lensed E modes into the linear order template, new cancellations take place at higher orders that actually remove power such that your delensing floor goes down to 1%. And notice how much more delensed this field here is than the alternatives. And the advantage of using this linear order version compared to the non-perturbative one actually is advantageous even for realistic scenarios. And that's what I'm showing in these plots. So in the x-axis, I'm varying the noise level in polarization. And in the y-axis, in the y-axis, I'm varying the noise level in the matter tracer. So if we focus on this left panel first, here I'm showing the fraction of lensing that's left over in the maps after delensing with a non-perturbative template. And notice that as your noise levels improve, you're removing more and more lensing until you hit this delensing floor here of order 10%. Now in the right panel, I'm showing the fraction of lensing left over after delensing with a linear template built from lensed E modes compared to the residual after delensing with a non-perturbative template based on lensed E modes as well. I notice that, for high noise levels, there's not much difference, but at some point, the linear version begins to improve on the non-perturbative one, even before the non-perturbative one has hit its delensing floor. And for CMB stage 4, which is the future generation of CMB experiments, perhaps coming online 15 years from now or 20 years from now, the improvement is that you will probably be able to remove 5% more lensing power if you use the linear version than if you use the non-perturbative one. So now I'd like to tell you about efforts to do this delensing operation on data from the Simons Observatory, which is currently being built in the Atacama Desert in Chile. So again, you will have this large aperture telescope doing the lensing reconstruction and delensing observations on large scales from these small aperture telescopes. So for SO, lensing reconstructions are going to improve on the state of the art, but we're still only going to be signal dominated down to scales of L of 250 or so. And we said earlier that it's actually scales smaller than that that are very important for delensing. So what do we do? Well, fortunately, you can combine internal reconstructions with external traces of the large-scale structure, which are highly correlated with lensing, such as the CIB. And you can see just how correlated the CIB is with lensing in this nice plot from the ACT collaboration, where they've overlaid the CIB, that's contours, on their lensing reconstructions, that's the gray scale underneath. And by playing this game of combining the CIB with galaxies and internal reconstructions, we can keep a high degree of correlation with lensing down to pretty small scales. That's what I'm showing in this plot here, where even though the internal tracer falls off in correlation on small scales, the CIB and galaxies really help you on those small scales. But ultimately, B-mode delensing is a difficult problem because the small scales that you need come from high redshifts. So for SO, forecasts suggested that this game of combining many such tracers could remove close to 70% of the lensing signal. And we're very happy to report that our more realistic pipeline tested on simulations that including homogeneous noise and masking is going to come very close to that forecast. And it's going to improve constraints on R by a factor of 2 or so. You can see here how, delensing really sharpens up this likelihood that speaking at the correct, well, sorry, in this case, there's no input R, but you're really reducing the uncertainty in your measurement compared to the case of no delensing. And yes, there are many challenges to this multi-tracer approach. One of them is uncertainties in measurements of the auto and cross spectra of the tracers. And this is potentially important, not just because forecasts may be slightly inaccurate, but because it's the true tracer lensing cross and auto spectra that determine the actual residual B-mode power spectrum. So insufficiently constrained tracer spectra can degrade constraints on R. For example, if the CIB cross correlation is in fact smaller than the fiducial model, that can cause an apparent excess of residual lensing B-mode power that you might confuse for a primordial component. And on the left, you can see that the shapes could indeed be dangerous for small signals, R of 0.001 or so. But the nice thing we're seeing is that actually when you co-add different tracers, those residuals tend to flatten out, and you're probably fine just to marginalize over a residual lensing amplitude. And the other thing that we're looking at is the impact of foregrounds. So the idea here, this is a different type of foreground from what I was describing earlier. So here we're worried about our own galaxy, which produces linearly polarized emission. And although they have a very different frequency spectrum compared to the CMB, such that you can actually remove them quite extensively, you are going to have residual dust and synchrotron left over in your CMB maps. And this will cause a bias, but this has been shown to be negligible for internal reconstructions of lensing and for delensing for CMB stage 4. But we pose the question of what about CIB delensing, which is going to be very, very important for the next decade or so. And I must say that CIB delensing was used in the first demonstration of delensing and has been used in pretty much every delensing demonstration to date. So here the worry is that residual amounts of CIB and dust left over in your foreground cleaned CMB fields, so both the B mode that you're trying to delens and the E mode that you use to build your delensing template, will correlate with the dust and CIB in your matter tracer and give rise to biases in the delensed power spectrum. In particular, we're worried about these BET or BEI, same thing, biases coming from dust and from the CIB itself. So we actually went into the data and, well, more like simulations, and estimated what residual fractions we should expect for the CIB maps that will be used and for the CMB maps that will be coming. And this let us estimate that actually in a standard foreground cleaning procedure, these biases will be very significant. So here I'm showing the relative size of the bias compared to the cosmic variance of both SO, which is the larger shaded region, and Lightbird, which is a futuristic space-based experiment covering a larger patch of sky. That's why it has less uncertainty. So in this standard foreground cleaning procedure, all these solid curves, which are for SO, different masking schemes in the CIB field so that you can mitigate the bias and stuff, as you can say, will be very significant. But the nice thing we find is that if you explicitly null the dust contribution to your high resolution E-mode observations, and you apply restrictive enough masking of the large scales of the CIB fields, these biases can be mitigated to levels where they're basically negligible for ground-based experiments, which don't really have access to these largest scales, and likely also for space-based experiments that will be able to foreground clean significantly better. And this deprojection, this nulling of the dust in the E-modes comes at very little cost in terms of delensing efficiency. So that's nice. We also looked at the bias coming from higher point functions of the CIB itself. Because there are no good simulations of the polarized CIB, we did this analytically in a minimal model where we assumed that source polarization angles are uncorrelated, but you can still have like shot noise-like terms where you have the three polarization legs coming from the same galaxy, that's this term here, or the E and B legs coming from the same galaxy correlating with another galaxy. And for any expected extent of point source masking, we find that these biases will be tiny. So that restores confidence in CIB delensing. But looking to the future, it's actually going to be lensing reconstructions obtained directly from the CMB itself that are going to have the highest signal to noise. And the reason is that as polarization observations get better and better, you basically have all the lensing B mode as unequivocal lensing information that you can use to reconstruct phi. So in this plot, you can see how the brown boxes get larger and larger to the point where for CMB stage 4, adding external tracers will only improve things by 5% or so, although there'll be a very useful cross-check. And one can show that the maximum a posteriori lensing reconstruction is equivalent to just an iterative application of the quadratic estimators. So anything that we learn from the quadratic estimators probably will inform systematic studies in the future as well. And ultimately, the limitation of B-mode delensing may lie with non-remapping corrections, so a curl effect that that lensing can also induce, but which is very small for the time being. It's at the order of 10 to the minus 4 of the total lensing power, and we won't be reaching that for the next several decades. So before I explain the last thing I want to talk about, which is a bias to internal delensing, let me remind you what the delensed power spectrum looks like. So you have your observation, you subtract from it lensing B-mode template, but to leading order, this is just this convolution of observed E-modes and your lensing proxy. And then it's terms like this, connected 4-point functions, that remove lensing effects such that you're left with some residual level of lensing plus experimental noise. But if you plug in an EB quadratic estimator, as is soon going to be the optimal thing to do, that is an estimator that reconstructs lensing from the E and the B polarization fields, then you get all these new couplings, 4 and 6-point functions of the lensed CMB. I'm sure Davide would really like these higher point functions. You get a suppression of power going just beyond a simple removal of lensing power. And this bias has been shown to be local, meaning that you can avoid it by just masking the mode in your lensing reconstruction that overlaps with the B mode that you're trying to delens. So you can see this in action in a little bit more detail in this crowded plot, but green is lensing plus primordial. If you delens that in a way that avoids these biases, you get the blue curve under this red. But then if you use an EB estimator, your bias is there, and you get this additional suppression of power. That's the yellow under the dashed black curve. And the important thing about this that got us interested in this problem is that actually this biased delensed spectrum has a significantly smaller variance than the unlensed one. So this bottom panel here shows you that in the biased case, the variance is down to 60% of the unbiased one. So if nothing happened in between to the primordial part, this would help you better constrain a primordial component, right? So we set out to model these biases analytically. We calculated many of those 4 and 6 point functions and came up with a model that agrees with the simulations extremely well. So here, this is the residual, and notice that it's well below percent level. And what this let us understand is that unfortunately, the bias couples to the primordial signal, and in fact, it suppresses it by a larger fraction than it suppresses all the other sources of lensing and experimental noise. So our model suggests a way of renormalizing the delensed power spectrum such that you recover unit response to the primordial part. And don't worry about the details of this equation, just know that DL is a complicated function between 0 and 1, such that all of this on the right is effective noise for the same level of primordial signal. So you lose signal to noise on a constraint, on a primordial component. And this is indeed what we see in simulations. Here I'm showing 25,000 simulations of inferences on a Simon's observatory-like experiment with an input tensor to scalar ratio of 0.01. That's this here. On the left panel is the R value that we recover, and on the right, the associated uncertainty. So if you don't delens, that's blue, you recover the correct central value with high variance. If you delens in a way that avoids the bias, you recover the correct central value again, and you do so with improved error bars. But interestingly, if you model the bias in the likelihood, you know exactly what's going on, you recover the correct thing, yes, but you do so at the cost of uncertainty. And for this particular experiment, it's as if you hadn't delensed at all. That's what this green line is shown. And of course, if you ignored the bias altogether, the bias was there, but you modeled the delensed spectrum as if it weren't there, you completely miss the large primordial signal screaming at you, and you're very sure that it's not there. And so this recommendation is that you always avoid these biases by masking overlapping modes, because that comes at very little cost in terms of reconstruction signal to noise, because those large angular scales don't give you much lensing information. And that's better than renormalizing or modeling. And this is going to be relevant for more futuristic lensing reconstruction techniques. And because I am aware that I might be going a bit over time, I'm just going to leave you with my conclusions. But thank you so much for having me. It's been a real pleasure. And if you have any questions, please ask.